Now let's discuss about the biological responses to biomaterials. The first is coagulation cascade and coagulation response to biological material that are directly in contact with the blood. So biomaterials in the current use, the example is many medical devices involve polymeric biomaterials. For example, catheters, coating for pacemaker leads, and contact lenses are made of polymers. And the common mode of failure in modern biomaterials are in two aspects. That's the first, the biomaterials that directly contact the blood or non-blood contact. So materials that contact blood will form of blood clots. That will be common problem and issue. And materials for non-blood contact will experience so-called a foreign body response that isolates the device from the rest of the body. So these are the example of polymer biomaterials, which is these polymers for cataract, polymer lens for cataract surgery, and these are catheters. So as a good example for biological response to biomaterial, as first as a vascular graft, which is artificial vessel. One good example is a Dacron and PTFE or Teflon is the most widely used for vascular graft. Currently, only large diameter vessels can be replaced with these synthetic grafts, because the problem is when this diameter is smaller grafts, they inevitably lead to clotting and vessel failure, and we see why. So this is still a major issue which hasn't been resolved yet. So how does this happen for vascular graft is shown here. So we have, let's say, the cells isolated and expanded to put it into a scaffold, which is shaped as a vascular vessel. So the cells grow here and then secrete extracellular matrix. So these cells are not the same patient. So we grow these and then we have to go to decellularization. So acellular, but only remaining extracellular matrix proteins, and we ship it and we can use it as a bioengineered vascular grafts. So these are the examples. So this is like 8 centimeter long and inner diameter is about 3 millimeter. So vascular bypass is to reconnect blood vessels. These are example. The problem of example is so the vessels are suffering from ischemia by atherosclerosis. So we want to replace it by vascular bypass. Good example is coronary artery bypass graft, or CABG we call in short. Or there are people who has let's say lower extremities in the legs, peripheral vascular disease such as varicose veins, and those can be replaced by vascular bypass. So I bring some example as scaffold-based tissue-engineered vascular graft, or TEVG, manufacturing process here. So the cells are extracted from patient and isolated so that these cells can be used for graft. So it's autologous. And the cells are expanded in culture, and it can be either mixed with a polymer scaffold directly, or these cells can be seeded to pre-made polymer processed porous scaffold. And these constructs can be matured in a bioreactor to become a tissue-engineered vascular graft. So how can we, in terms of research aspect, compare this with our natural vascular graft, which is used using our own veins in a saphenous vein. So I put a picture here. So the patient's own saphenous vein, and these big and small veins have been used a lot for coronary artery bypass graft. And so we can compare this with this tissue engineered vascular graft. So these data is interesting to see. So we call coronary artery bypass graft CABG. But the saphenous vein is a field circle, and PTFE engineered ones are empty circle, which goes down over the years. You can see that graft patterns is deteriorating, and the other femoral pop above knee, and this filled and unfilled rectangles. You can see this, and it's not too bad. It's a little worse. And another femoral distant artery, and this one also, this triangles, still it's lower. So we can see still this patency rate for small diameter vascular bypass procedures. It probably is still better to use saphenous vein instead of this PTFE tissue engineered conduits. So for this biomaterial that are in contact with the blood, there's a very important aspect, which is a blood clot formation that we call coagulation. And this is a result of cascading chemical reactions of plasma protein, which include clotting factors. And this looks a little complicated, but it's very important. There are multiple Nobel Prizes came out of this blood clot cascade. So this is an example of picture that inside the blood clot, there are fibrin mesh, insoluble meshes formed, which captures or trap red blood cell, and the platelets who made this are activated here so that they form a blood clot. And this is called the coagulation cascade. And as the formation of blood clot is a very well regulated series of interrelated and enzyme mediated reactions, because this is very important for our life to stop bleeding and loss of blood. So you can see there what causes this blood clot. There are two causes. One is intrinsic pathway and the other is extrinsic pathway. Intrinsic pathway is caused by a charged surface, such as exposed extracellular matrix. Usually the blood flows inside a vessel, so that's covered by endothelium. But for some reason, if the endothelium is gone, and then underlying basement membrane, extracellular matrix is being exposed, that can trigger this blood clotting, because that's an indication. In terms of biomaterial point of view, biomaterials, which is direct in contact with the blood, it's known that there are the proteins first adsorb. It covers this biomaterial, and those protein coating will likely to cause intrinsic pathway of blood clot. So that is a big risk. The other extrinsic pathway is activation, is coming from tissue injury and resulting vessel damage. Then we have a risk of losing blood and bleeding. So extrinsic pathway is activated and start to run blood clotting. So this is a map of this intrinsic pathway and extrinsic pathway. From the surface, charged surface, there are enzymatic activation. You see small a means activation. And that goes, and extrinsic pathway is coming from vascular injury and tissue factor, and it makes this factor X2 activated one. And the point here, important thing is prothrombin become converted into thrombin, and that goes back into the original, which makes a positive feedback that to make this process real, quick, and amplification, so that it makes eventually the soluble fibrinogen into fibrin polymer and cross-linking fibrin polymer, such that these are insoluble and it forms a blood clotting. So you can see these as a multiple well-regulated steps as kind of cascade. So we call it coagulation cascade, which is the formation of blood clot. And I want to show this, the good and bad aspects of this formation of blood clot, which is our intrinsic protection mechanism for our blood, and preventing infections, microorganisms getting into our body. But on the other hand, this clot inside the blood vessel may cause health issues. So the end point of coagulation cascade is the formation of cross-linked mesh of the protein fibrin. And let's look at these blood clots. So if there's an damage into the vessel, then the tissue activated blood clotting. So you see the platelets and RBCs leaking out, broken blood vessel wall. And in the end, this fibrin mesh will form to trap RBCs, and the platelets are activated and try to block it. And then later on, it'll wound healing. So the end point is a formation of the protein fibrin, and the fibrin cross-linking is producing a solid material by trapping red blood cells and platelets within a protein-rich network. And that will closes the area of damage and stops bleeding. So that's very important. This electron microscopic graph shows clearly these fibrin mesh and trapped RBCs, and the platelets are activated. The problem is there are also unwanted formation of clots, such as a formation of clot which will shed as a traveling clot, which we call as an embolus. That can block small vessels, and which can impede blood flow to the tissue and tissue ischemia, and this can lead to, if it ends up into the brain, it can lead to a stroke, or if it ends up lodging into the lungs, it can cause breathing problems. So let's look at review a little bit. So positive feedback loop due to thrombin and the outcome of the formation of fibrin. Up to now, no biomaterials inert, which is still a big problem for us. And intrinsic pathway is activated by presence of charged surfaces, such as blood contact with the collagen, fibers in the subendothelium. Yes, endothelium is, let's say, exposed. Subendothelium, there's a basement membrane which contains a collagen type 4, or with a biomaterial. So biomaterial can cause an intrinsic pathway of blood clotting, and this requires a number of clotting factors and mineral calcium ions. An extrinsic pathway is activated by a trauma to vascular walls and surrounding tissues, and that clot formation is in response to tissue injury and vessel damage. So next time, we will discuss about implanted biomaterials, which is not directly contact with the blood, that will cause foreign body reaction. Thank you for your attention.